Hello everyone. This is Jinzhe from Rutgers University. I'm a PhD student in New York School. Today I'm happy to introduce DeePMD-kit software, a powerful, effective, user-friendly, flexible, and free platform for deep language models. So let me introduce the background. There are different levels of computational models, and here is DFT level. It is accurate but very slow. And classical MD, it is fast but not accurate. And so neural network potentials is coming out. In 2007, the first neural network is proposed, and it fits DFT level data as fast as classical molecular dynamics. And there are a lot of popular neural network potentials. However, at that time, there is not open source software to implement these potentials. So in 2017, the initial version of DeePMD-kit is proposed, and then in the past 5 years, more and more research and developers are attracted by DeePMD-kit, including me. Firstly, I'm a user of the DeePMD-kit, and then I think it's a very nice software, so I joined the development team. And now, DeePMD-kit has released the version 2.1.3 with about 900 stars and have 41 contributors, and it has been used by over 100 papers by 400 authors from 13 countries and 126 issues, and published in 65 journals. And we can see this is the number of publications, and it go up. And here I take about 50 applications of the DeePMD-kit in different areas. It is including gate phase reactions and also in solution, and some materials, different materials, and also some water applications. And most of them are published in the top journals like Science, Nature Communications, and so on. So let's talk about the DeePMD-kit itself. It is a Python and C++ mixed software, and the Python API is based on the TensorFlow version 1 Python API, that is tf.compact.v1, and the command line interface is based on the Python API. It is used for training and interface. And we also have some custom operators, which is based on the TensorFlow C++ API. This is written by C++, so we also have a C++ library, and which is implied CUDA and ROM-C library. And also we have a C++ API it is used for MD softwares. We know C++ is much faster than Python. So we use C++ API for different MD software like NAPS, GoMax, SciPy, and OpenMM, and all of them are open source. And here I can introduce the models implement in the DeePMD-kit. We use the TensorFlow graph to implement different models. And the input tensor is the ultimate coordinates and enactments. And sometimes it has a box. And then it passed to a descriptor. We support different descriptors. I will introduce later. And then descriptors are passed to the fitting neural networks. And sometimes we have a modifier to support the long-range interactions. And the output of the model is energy force is the graduate of the energy, and sometimes it's viral. And also we support to fit dipole and plausibility. This is the model graph, and for training we also have a trainer graph. It has the loss. The loss function is defined as the output mean square error. And sometimes we also want to fit both energy and forces, and our loss function supports this thing. And with the learning rate, we can optimize the model. Here I take an example. The two-body embedded descriptor in the DeePMD-kit. It generates the coordinates materials from the ultimate coordinates and enactments. And this is implemented by the custom operators because TensorFlow doesn't have such thing. And then with the coordinate materials, we pass into a neural network. This is different from other software. Other software usually only have one neural network in their model. However, we have two neural networks. One is for the embedding descriptor, and another for the fitting neural network. And with output neural network, we then do a mathematics thing to get the final descriptor. And here is a second example to make an extension of the two-body descriptor to make it integrated with the QMMM. Here, we correct from the low-level QMMM to high-level QMMM, and we only fit the QM part and range of the QMMM part. So it is very fast, as only a small part of the system is fitted. And we do some modifications to the descriptor. And here we use QMMM plus our deep potential to fit the system in the solution and do the MD and the PMD to compute the free energy surface. Then I want to talk about the user-friendly about DeepMDkit. First, it can install in 5 minutes with the support of the with the package of the Coda, Docker, and Pipe. Both of them are supported, and also it supports the GPU packages. For the automatic inference based set, we know a GPU card have memory to limit the base set of the inference model. If you inference something with the large base set, you may get a out of memory error. So here we have a sketch workflow to gradually increase the base set until the out of memory error reaches. And the third thing is we have a GitHub discussion to ask questions, and I will answer questions on it, and anyone can search the previous questions, and they may get the correct answers. And also we have documentations for the parameters and IPS. This is supported by SciPy and Dolphin, and the Arch is a new software that we developed to support to document the different parameters. And last one is we have a web-based guide to generate user input JSON file. This is the JSON file is very hard to is not designed for the human beings, so we have a visible tool to generate it. Then I want to talk about the performance of DeepMDkit. With our custom operators and also the TensorFlow native operators, we support OpenMP, CUDA, IOCM, and one API to support the different hardware. And it also supports MPI when you training on multiple GPU cards, or also to run as MD solutions. And someone research also develop a new hardware to run solutions, run DeepMD-kit solutions. Nowhere is called NVN FPGA hardware. Also, we support model compressions. It uses a fifth order function to fit the neural network, and then to make a table to fit the neural network. Then it is faster than neural network. It is not for training, but for MD solutions. So we have some benchmark of the DeepMDkit. The first line is we perform the solution of the 70 billion atoms on a supercomputer cluster, and it has very less performance, and also this is 3.4 billion atoms. This is on Summit with 27 kilo V100, and for a single 3080 Ti card, I think it's very common. It also has a good performance to perform the large systems. The last one is the hardware to design for the DeePMD-kit molecular dynamics. Let me talk about flexible. Firstly, it is integrated with third-party software. We provide C++ API, Python API, and command line interface. C++ API is used to integrate with the different MD software. And Python API is used for Python packages. Deep data is something that we use to converting format from the initial software format to our format. And ASE is can use for it has some useful tools for molecules. And the command line interface is usually useful. Usually used for workflow software. DeepGenerator is the software we developed to do the active learning cycles to training deep potential models. And also, we have a custom described API to for someone that maybe if someone want to implement a new descriptor or new something else, they may use this API without the modification to the DeepMDkit itself, and it can be used to develop a new descriptor. Last, I want to talk about DeepMDkit is an open source communication repository, and it is under the LGPL 3.0 license, and it is open source on the GitHub. The DeepModeling community also have some nice software in different areas, and maybe each use maybe interesting. Interesting, and then we here I have installed DeepGen and Deep Data. The DP Dispatcher is a software that can submit your job to HPC to run your jobs, including the training the model molecular solutions or calculate the forces on another machine, and it is useful for the workflow software. DMFF is a software to build some common force field, and then we also have some DFT software and a software for computations, and a workflow software to do some automatic workflow, and the last one is a mathematics software. Okay, so I want to thank my PhD advisor, Dan York, and also the NIH grant, and also all the contributing to DeePMDkit. Here is the full list. Okay.
All right, thank you for the talk. Do we have any questions?
So thank you. Whoop, that's loud. Thank you for your talk. I was wondering, you mentioned your loss function was based on the mean square error of the things you're training on. And if you train on energies and forces, do you use equal weights of those contributions to the loss, or do you reweight that somehow? And are you kind of normalizing it, or how do you deal with the different scales of energies and forces, like in general? So, like, your energy error will likely be on a much different scale than your force error, right?
Oh,
Do you kind of account for that, or?
no, the energy error is times to something. Times a number, and also the force error is also times a number and the sum of them.
Any other questions? Any other questions? I have a question. I have another question. So in the beginning, you showed there's integration with different molecular dynamics software. How do you handle the non-bonded terms in those? Because let's say if you look at like OpenAI, is it possible to use the non-bonded from these neural networks, or you have to sort of use the classical non-bonded terms?
You mean the non-bonded in the?
So with the sort of MD engines, many of them, it's like hard-coded. You sort of need the non-bonded. There are sometimes issues of using non-bonded from these neural networks potentials in these engines. Have you encountered that? Like the charges and Leonard zone terms.
I think the model can also fit the non-bond potential.
And and how do you address the non-bonded issue in these neural networks?
I mean, it has a cutoff radius. Any interaction within the cutoff radius will be fitted by the model.
Okay. And I guess another question I have, what's the difference in speed of using these neural networks versus the classical force fields? Is there a difference in speed, or are they equally fast?
Sorry.
So speed, right? Because sometimes the neural network potentials can be slower than the classical force fields. What's the comparison in speed that you get from these neural network potentials and the classical? Have you done a comparison?
Comparison.
Okay, we can take it offline. Okay. Thank you again for the great talk.